Hello, hello. This week's Fiddler, it's kind of an easy one for someone that's done a lot of statistics. So we're going to start out by stating the question. So suppose I have some squares that I'm painting, and those squares are just all adjacent in a line, and each one is either going to be red or blue with 50% probability. And I'm pretend somehow we could paint this line infinitely long. I want to ask what the average cluster length is, which by cluster length, I just mean the length of adjacent squares that have the same color. So in this example, we have red, blue, red, blue, red, 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 blue, blue, red. The average cluster lengths are going to be one red, then one blue, one red, one blue, three reds, uh, two blues, one red. So you just take the average of these seven numbers, 1, 1, 1, 1, 3, 2, 1. That's going to be our average cluster length for this particular sample. So because we have an infinite time horizon, I'm just going to reframe this question to a much simpler question, which is what is the expected length of a cluster? And those have to be the same. And the expectation is just taking the sum over all possible outcomes of the outcome you care about. So our x in this case is the length times the probability of getting that length. And in general, the expectation is a kind of a statistical or probability operator that tells you something like if I were to do a sample of something an infinite number of times, what would be the average number, the average outcome, essentially? There are other kind of interpretations of it, but this is essentially the way I'm going to be using it. And I need to briefly talk about this idea of independence, which just means that one sample doesn't have any bearing on the other sample. And if I had some sampling error, I might have sampling error in that particular thing, but if there were no sampling error, which there would be if I have an infinite number of samples, my expectation is going to be the same as the actual average I would get. So because the way this problem is set up, the length of the first cluster is totally irrelevant to the length of the second cluster, right? So we do end up getting independent cluster lengths on this infinite distance horizon. Then these two statements of the problem are exactly the same, right? I can go back to this line and think, okay, well, the first cluster has length one. Does that impact my second cluster? No, because the second one, if the first cluster is length one, that means if it starts red, the next one is blue. What's the length of the next one? It doesn't matter at all that the first one was red when I think about that. We're just going to keep going and say, okay, is the next one blue? Yes or no, and keep going until you hit a red one. And what you did before doesn't matter at all. So we could think about this as independently building this and each sample being subsequent in space here as opposed to in time, but it's exactly analogous here. So how do I get the expectation? Well, I need to know the probability of getting any particular number of clusters. So what's the probability that the cluster has exactly length one? Well, that's going to happen if my second one doesn't match my first, and that's going to happen with 50% probability, right? If I start with red, what's the probability that my next one's blue? It's 50%, right? If I start with blue, what's the probability that my next one's red? Also 50%. So no matter how I start, the probability of not growing is just 50%. What's the probability of getting length two? Well, now I need the second one to match, but the third one not to match. So that means the first one matches, that happens probability 50%. The second one doesn't, that also happens with 50% probability. So now we're at a probability of 25% total. And this kind of continues on. If I want to know the probability of getting length n, that's just 1/2 to the n, where, n is the length that I'm worried about. And so if I take the expectation here, it's just the sum of all possible n's of n, which is the outcome we care about, the length, times the probability, which is times 1 over, and here I'm just dividing by 2 to the n. And this turns out to be 2. I'll do a brief explanation of why that's true, although, so how's this going to work? So a much more well-known series than the one I just did is the sum of x to the n, where x is somewhere between 0 and 1. And if I have to be a little bit careful what I'm summing over. I don't have, from n from what to what, right? I don't say that here. In this case, it's n from 0 to infinity. And we'll talk about how that might matter in a second. But if I take x to the n, where x is between 0 and 1, and n is going from 0 to infinity, then this series is going to total 1 over 1 minus x. This is a fairly well-known geometric series, and I've even explained it better in a previous Fiddler puzzle. So you can go back to that or find one of, I'm sure, millions of videos that explain why this holds true. What I'm going to do is now take the derivative with respect to x of both sides. So the derivative of x to the n is just n times x to the n minus 1. And doing that over the sum of all possible n's isn't going to affect the derivative of each individual component. So I'm also going to be summing from 0 to infinity of this section. And then the right side, if I take the derivative again with respect to x, is 1 over 1 minus x squared. So this is kind of a chain rule thing. If you don't want, you can just plug that into Wolfram alpha and see what the derivative is. But this is what you get. And now if I take x equal to a half, why am I picking x equal to a half? Because that's going to get us something like what we want, right? So if I take x equal to a half in this equation, the right side is 4, and the left side is very close to what we wanted, right? Remember what we wanted is n over 2 to the n. What I have instead is n over 2 to the n minus 1. So this is really close to what I want. So to make this what I want, I'm just going to divide both sides by 2. And if I do that, the left side becomes what I want, my right side becomes 2. So the sum is what I want it to be. Okay, so instead, let's suppose that we have 2 rows instead of 1 row. What's the new average cluster length? So we have something like this where we have red and blue being painted in 2 different rows, but the clusters can cross rows. So for example, in this bottom left, we've got a cluster of 6, a couple ones up top, a 2, a 4, right? So those are the cluster lengths. Now, this is where I have to issue an apology for my last video, which was absolutely wrong. I got the number, I got to my conclusion based on a simulation that I had run that turned out to have a coding error. So it's just absolutely wrong. The intuition behind what's going on is actually, I think, still correct. It's just that they don't cancel out. It's not the case that the offset from the being able to crowd out into the other row, that does limit the other clusters, but it doesn't limit it by as much as you gain by having new clusters. And so we're actually going to redo this a different way and in a way that is much easier to extrapolate going forward. And so I want to instead ask the question of what's the probability if I add a new row or a new column, then what's the probability that I'm going to get a new cluster? And we're going to still think in the 1 row example. Well, it's just 50%, right? If it's the same color, we don't get a new cluster. And if it's a different color, we do get a new cluster. And so as I go, as the number of columns I make goes to infinity, then the number of clusters I'm going to end up with is, however many, this fraction is actually wrong. It should be n over 2 plus 1. And so if I then take the total number of cells, which is n, and divide that by n over 2 plus 1, that's going to be 2 as the average length of our cluster as n gets really, really large. So using this kind of an idea, we get the same result of 2 as the average length. But this is going to generalize much more nicely to a larger number of rows. So now let's go back to the 2-row example. But now we have to think, okay, I actually have 2 possible starting points, and each are going to have kind of a different outcome. Either the end of what I currently have painted has an end that's 2 different colors. The top color is different from the bottom color. So, or they have the same color. So the top and bottom are the same color. If we're in that latter case, where they're the same color, which has a 50% chance, or there's a 50% chance that those 2 endpoints are the same color as opposed to different colors, then there's going to be a 3/4 chance of adding a cluster, right? So if I, so let's say the ends were both red. There's a 3/4 chance that at least one of the next pair of squares is blue, right? And then there's a 25% chance, or 1/4 chance, that it's double red again, and so there's no new cluster. But any other case is going to add exactly 1 cluster. And so in expectation, we're going to add 3/4 of a cluster in this case. But if the end of the grid has one of each color, so let's say a red on top and a blue on bottom, then there's a 75% chance that there's no new cluster at all, right? Because if they're the same color, if the next 2 are the same color, I'm not adding a new cluster because that's going to connect to the previous one. It will cut off the one that's not repeated, but it's not going to add any new clusters in that moment. But there's a 25% chance. So if it's the case that the new colors are swapped vertically from the old colors, then I'm going to end up with not just 1, but 2 new clusters. And so if I want the expected number of new clusters, it's, 0 times 75% chance plus 2 times that 25% chance, or a half. And then I can get the total expected number of clusters, which is 1/2 times 3/4, 1/2 being the probability that we're in the state of the world that the colors match. And in that case, there's a 3/4, there's an expected 3/4 cluster gain from the next column. And I'm going to add to that the 50% chance that we're in the state of the world where we're starting with different colors, and then the expected number of clusters there is a half, and then we end up at 5/8. So for every 2 squares that I add in expectation, I'm adding 5/8 clusters. So my expected cluster length is going to be 2 over 5/8, which is 3.2. So that is the actual answer to the extra credit, not what I had in the earlier video. So apologies for misleading you. And big thank you to Tim Vermeulen, who pointed out my mistake and actually gave me this method for finding the correct answer. So big thanks to them for their help. And thank you for watching. And hopefully if you saw the old video, you can come back and see this one too and see the correction. Thanks. Bye.